Imagine training a massive graph neural network on a trillion-edge graph, using just a single commodity server. No fancy interconnects. No caching. No remote feature fetches. Just raw, efficient training, accelerated by a radical idea. What if we never sent neighbor data across partitions at all? This is the core of Grappa, a new distributed GNN training framework that eliminates cross-partition communication entirely. Instead of shuffling features and activations across machines every iteration, Grappa trains each partition in isolation, only exchanging gradients. And yet, it achieves up to 13 times faster training than state-of-the-art systems, with better accuracy, especially for deeper models. Let's dive into how this works. The problem: communication bottlenecks in distributed GNNs. Graph neural networks are powerful tools for learning from complex data, social networks, molecules, recommendation systems. But as graphs grow, billions of nodes, trillions of edges, training becomes a nightmare. In distributed GNN training, we split the graph into partitions across multiple machines. Each machine trains its own subgraph. But here's the catch: message passing requires nodes to aggregate information from neighbors. When a node's neighbor lives in a different partition, the system must fetch that neighbor's feature or activation across the network. And this happens at every layer, every iteration. As models grow deeper or partitions increase, this remote fetch overhead explodes. It dominates training time. Even with high-speed interconnects like NVLink or RDMA, once data leaves the GPU island, it falls back to slower PCIe or network links and performance tanks. Caching helps, but it eats memory. High-quality partitioning reduces edge cuts, but it's expensive to compute and hard to balance. Mini-batch sampling reduces computation, but not the need for remote data fetches. We're stuck in a trade-off: high capacity versus high communication cost. The solution: gradient-only communication. Grappa flips the script. Instead of fetching neighbor data, it locks each partition in isolation. No cross-partition feature or activation exchange. Only gradients are synchronized across replicas. This is gradient-only communication, a radical data parallel strategy that removes the dominant cost: remote neighbor traffic. But isolation introduces a new problem: sampling bias. A node only sees its local neighborhood. Its gradients are biased toward that local structure. If we just average them naively, we lose accuracy. So Grappa solves this with two key innovations. Innovation 1: dynamic repartitioning. Grappa doesn't stick with one partitioning forever. Instead, it runs training in super epochs, blocks of several regular training epochs. At the end of each super epoch, it repartitions the graph, shuffling nodes and edges into new partitions. Why? Because even if a node never sees a neighbor in one partition, it will eventually be in a new partition where that neighbor is local. Over time, every node gets exposed to its full neighborhood. This is far more efficient than constant remote fetches. The cost of repartitioning is linear in input size and number of super epochs. The cost of exchanging intermediate activations: exponential in depth and number of cuts. So Grappa trades expensive per-iteration communication for infrequent, low-cost repartitioning. Innovation 2: coverage-corrected gradient aggregation. Even with repartitioning, some neighbors may be seen more frequently than others, especially in skewed graphs, leading to sampling bias. Grappa corrects this with a batch-level, importance-weighted gradient aggregation, inspired by importance sampling. Here's how it works. For each batch, Grappa tracks how many times a node's neighbor was present in the local partition. It computes a correction factor based on the ratio of global degree to local degree. Then, it scales the batch gradient by this factor before averaging. Formally, the corrected batch gradient is theta L batch C equals C times average of local gradients, where C equals average of global degree / local degree across all sampled neighbors. This estimator is asymptotically unbiased under mild conditions, meaning, as the number of super epochs grows, the correction converges to the true full graph gradient. Even better, among all possible scalar corrections, this one minimizes the mean squared deviation from the ideal node-level correction. It's the best possible batch-level approximation. And for even better stability, Grappa includes a shrinkage variant, using a harmonic mean-like correction that reduces gradient magnitude, acting like a built-in form of gradient clipping. This combats overfitting and improves robustness. Why this works so well? Let's break down the mechanics. Isolated training is like applying dropout to the input layer, randomly removing parts of the graph. This improves generalization, especially in deep models. Repartitioning ensures long-term neighborhood coverage. Coverage correction recenters gradients toward the full graph objective. Together, they preserve convergence properties of standard GNN training, while slashing communication. And because partitions train independently, Grappa supports phase parallel execution. You can train only a subset of partitions per phase, saving memory. This allows single-machine training at the trillion-edge scale, something no other system can do without massive distributed memory or out-of-core tricks. Real-world performance: 4 times faster, 13 times faster in some cases. Grappa was evaluated on real-world and synthetic datasets: Reddit, OGBN papers 100M, RMAT graphs up to 1.1 trillion edges. On 16 partitions, Grappa achieves 4 times average speedup, up to 13 times over DGL, the closest baseline. Why? because it eliminates cross-partition traffic entirely. While DGL's epoch time grows with depth and partition count, Grappa scales nearly linearly. Even on massive RMAT36, 1.1 trillion edges, Grappa trains one epoch in just 3.6 hours on a single V100 machine, using phase parallel mode. And accuracy. Grappa outperforms DGL on deeper models. While DGL's accuracy drops sharply with depth, down to 51% on 4-layer models, Grappa holds steady around 67%. Why? The dropout-like nature of isolated training reduces overfitting. It's not just faster, it's smarter. Ablation study, each piece matters. Grappa's components aren't optional. Remove gradient correction. Accuracy drops from 93.26% to 82.84% on GCN3. VIX partitioning. Accuracy falls to 84.64%. Allow 50% remote sampling. Still worse than Grappa. Even though full graph access seems better, isolation plus correction outperforms naive full access, thanks to implicit regularization. And overheads. Minimals. Partitioning, 2-3 seconds per 64 partitions, far faster than METIS. Switching partitions, only 10-12% of total training time, even at 64 partitions. Grappa's design is efficient, lightweight, and practical. The bigger picture, model-agnostic, scalable, future-proof. Grappa works with any GNN architecture, Graph Sage, GCN, GAT. It supports both full graph and mini-batch training. It runs on commodity hardware, no need for expensive interconnects. It's not just faster, it's simpler. No complex caching, no intricate partitioning heuristics, no dependency management. And it's compatible with existing tools. Grappa integrates cleanly with PyTorch via a single gradient scaling hook. Conclusion, a new paradigm in GNN training. Grappa proves that you don't need to move data to train GNNs efficiently. By embracing isolation, correcting for bias, and repartitioning strategically, you can train billion and trillion edge graphs on a single machine without sacrificing accuracy. It's a new paradigm, gradient-only communication. It's faster, it's scalable, it's robust, and it's open-sourced. If you're building the next generation of graph learning systems, this is the direction to go.